Everyone. I am Kritika Rathore, and today we are going to discuss a very interesting topic, which is parallel coordinates. This video is completely designed and presented under the guidance of Dr. Anita Mahajan ma'am. Today's our topic is parallel coordinates. Let's begin with a simple question: how do we visualize data that has more than three dimensions? First, let's discuss the points that can be covered and that we'll be going to cover in this video. The title and the overview of the topics, introduction, the topic in details, summary, resources for the further study and references. Introduction. In modern data analysis, we often deal with data sets that have many features and dimensions, far more than a data visualized in a standard 2D or 3D graphs. This presents a challenge. How do we see relationships, patterns, or trends in such data? Parallel coordinates is a method developed to solve this. It transforms table of high dimensional numeric values into a form that can be visually inspected. This technique enables analytics to grasp that the structure of the data at a glance is invaluable in domains like machine learning, bioinformations, and finance. This is a traditional 2D scatter plot. What are the parallel coordinates? In 2D graphs, we use x and y axis. In a 3D graph, we add the z axis. But what if we are working on a data set that has 20, 50, or even 100 dimensions? That's why the parallel coordinates come into the play. In parallel coordinates, each information is represented as a vertical axis. These axes are placed parallel to each other. Each data point is presented and represented as a line that interacts each axis at a point that corresponds to its value in that dimension. What is parallel coordinates? So, how is they useful in the computer graphics? Well, think about the rendering of a complex 3D scene. Every object in the scene might have multiple attributes, color values, RGB, lighting parameters, for example, intensity, direction, ambient, material properties, for example, roughness, spectacularity, and reflexivity. You are dealing with a multidimensional data if you want to tune your shaders or lighting system, or if we are analyzing the scene. The history and the origin of the parallel coordinates. The concept of parallel coordinates was introduced by Alfred Inselberg in 1980s, originally designed as a method to study geometry in higher dimensions. It was later adapted by the data analysis. Inselberg works laid the groundwork for applying geometrical visualization to statistical data, enabling a more interventive understanding of complex data sets. Why we use the parallel coordinates? The traditional plots struggle as dimensionally grows. Scatter plots effectively handle up to 3 to 3 dimensions. The datasets with 10, 20 or 100 features exceeded scatter plot capacities. Parallel coordinates assign each dimension in its own vertical axis, and each observation is drawn as a line intersecting all axes at its values. This facilitates detection of patterns and relationships across many variables. Structure of a parallel coordinates plots. Multiple vertical axes are laid outside of the horizontally. Each axis corresponds to one feature or variable. Actually, how it works. It creates one vertical axis for each variable, scale through or normalize the data, and draw a line for each data points. The basic example of a scatter parallel coordinate plot is, just imagine we have a data set with attributes like age, annual income, spending scores, and credit card scores, and the parallel coordinates. Each of these includes for this own axis. Simple words, how do we read the parallel coordinates plots? Follow a line from leftmost to the rightmost axis to the read and observation. Each intersection point indicates the value of the feature for the observation. Groups of lines tracing a similar path imply a correlation or cluster. A line that diverges sharply from the rest flags a potential outlier. The angles or slope between two neighboring axes visualize a relationship. Many lines and the sloping from the low to high or high to low suggest a negative or a positive correlation. Axis scaling is the one of the major topic that includes features can have different scales like income in 1000 versus scores in 1 to 100. Plotting the row values lets a large scale variable visually dominate. To avoid this, each variable is normalized via minimum or maximum scaling. Normalization makes every axis span the same range. Equal scaling ensures all features carry the same visual weights for fair comparison. The brushing and interaction is an interesting topic in the parallel coordinates. It involves the brushing lets you select the range from the data from one axis. For example, the brush high income customer to see their credit scores and spending patterns. That turns a static plot into a dynamic, exploratory tool for deeper insights. The axis reordering. This is more flexible axis reordering enables intuitive exploration of data relationships. This order the axis affects to plot readability. The handling the categorical data. We have the different types of data, but the handling the categorical data is the major part in the parallel coordinates. These are primarily designed for numerical data but adaptable for the categorical data. The categorical data can be encoded numerically, for example, 1, 2, 3, and 0, with the separate axes. The color coding can help to distinguish the group and line. For example, encode gender as 0 and 1, and then apply distinct color for each category. Clustering and grouping. Parallel coordinate works on this parameter like lines following similar path across all axes indicate a group of cluster. Color coding, cluster 8, and the visual segmentation of the grouping of the data. Outlier detection. Lines that dramatically deviate from common point represent outliers. Outliers may indicate data errors, exception cases, or novel discoveries. In customer dataset, outlier could point to potential fraud. In sensor data, outlier may signal equipment malfunctions or failures. Parallel coordinates plot make these deviations visually prominent. The use cases of the parallel coordinates are in data science that helps to identify the redundant or highly correlated features. This assists in detecting data equality and issues such as outliers or missing value patterns. The use case is in finance also. This helps to facilitate risk assessment through the comparison of volatility and risk factor. The use case in health and biology. The medical datasets include numerous indicators, for example, blood pressure, heart rate, glucose level, and cholesterol. Parallel coordinates assign each indicator its own vertical axis that enables healthcare professionals to observe how multiple indicators vary together. In genomics, thousands of gene expression levels can be plotted simultaneously. In cybersecurity, the parallel coordinates assign each parameter to separate a vertical axis. It involves tracking multiple parameters, for example, login, frequency, session duration, IP address, and port access that suppose early detection of the potential security threats and breaches. The advantages over everything is highly dimensionality, patterns recognition, anomaly detection, interactive capacities, common representation. Now, as we discuss the advantages, there are few limitations of the parallel coordinates that involves overplotting, interception difficulty, dependence on scaling, order sensitive and categorical complexity. The summary of the parallel coordinates involve the powerful tool for the multivator data. To wrap up, parallel coordinates may not draw your model or render your scenes, but they help to understand your scene better. What parameters are doing, how they relate, and how to optimize them. In computer graphics, especially the production and simultaneous environment that insights save hours of trial and error. The best practices involve normalize the data, limit dimensions, feature color and feed filters, interact dynamically, and label carefully. The references here used is the comprehensive theoretical and practical guide which was given by Alfred Insenberg, the online resources EDX Dynamic for data visualization. I read the blogs and tutorials by the data visualization expert, for example, flowing data and visualizing data. Here is a demonstration you can view to click on this image. The acknowledgement I would like to express my sincere gratitude to Anita Mahajan ma'am for the subject teacher of the computer graphics and visualization for providing me such an opportunity to explore and present this topic. I'm thankful to my college and classmates and everyone who supported me during the preparation of the presentation. Thank you so much. And if you found this video interactive and useful, do comment and share.